Okay, so at this point you should have watched the apple and the moon, moon and the apple, moon, apple, whatever. And I wanted to just talk for a little tiny bit about that whole thing Newton did where he showed that gravity we have on the surface of the Earth is the same as the gravity that holds the moon in orbit. So the equation we came up with there, at least for the magnitude of gravitational force, is, let's see, it looks like this, G, and then if you're talking about the Earth's gravity, then M sub E, this ME here, is the mass of the Earth, and little m is the mass of whatever object you're talking about, and then you divide by the square of the distance between the object and the center of the Earth. So if it's the Earth, say there's the Earth, and the radius of the Earth is R sub E, then you have an object of mass m up there. Then that Fg is, well, that's what we call m times little g, is the force due to gravity on the surface of the Earth, right? So m times little g, and we plug in big G, me, and little m over radius of the Earth squared. Okay, and when you plug in the correct values for capital G and me and capital RE, what you get is, of course, you can cancel out the little m's, and you will get that little g is g times mass of the Earth over radius of the Earth squared. Okay, so that is fine for gravity on the surface of the Earth. What we want to do now is show that this 1 over r squared thing works. So what he's saying, what Newton was saying here, is here's the Earth, and it has its its mass, okay, and then the moon is orbiting in a circular orbit, and we will call the radius of that r, little r with a subscript of m. And so what Newton was saying is that the acceleration due to gravity should be proportional to 1 over the square of your distance from the Earth's center. Sorry, that's supposed to be a little r there. This drawing thing does not work perfectly. So where you get what you get here is, if you sort of do all this, you can say that acceleration due to gravity, which is a function of your distance from the Earth's center, is going to be equal to capital G times mass of the Earth over r squared. Okay, whatever that is. And so what he wanted to show was that this would then give the correct centripetal acceleration for the moon. So the moon is going in its orbit, okay, and it's got some speed it's going around the Earth at, and we want to find what will its acceleration be. So if the acceleration of the moon is the acceleration of gravity at rm, the distance of the moon from the Earth away, then it should follow this relationship, and we should get acceleration of the moon in its orbit should be, let's see, so I'll just plug in what we had there, capital G, mass of the Earth over rm squared. And so we just want to verify this is true. So what we get here is, first of all, we need to actually plug in some numbers. So let's go with distance from the Earth to the moon is 384.4 times 10 to the 6th meters. Okay, so it's 384,400 kilometers, which means it's 384,400,000 meters. A lot. Okay, and we know that distance from the Earth to the moon is approximately equal to 60 times the radius of the Earth. That's something they mentioned in the video that's been known since antiquity, and it was in fact known to the ancient Greeks. So when we plug that in, and let me just do my little color change there. So we take this here, and we plug it into here, then what we get is that the acceleration of the moon should be equal to capital G times the mass of the Earth over, and it should be rm squared, and so that's going to be 60 squared times the radius of the Earth squared. And you'll notice that this GME over RE squared is also this, right here, and it's equal to little g. So what we can get there is that the acceleration of the moon is equal to our surface gravity on Earth divided by 60 squared. Okay, so let me move on. And acceleration of the moon, centripetal acceleration of the moon is equal to little g divided by 60 squared, which is 3,600, and that is going to be equal to 0.002725 meters per second squared, which is also 2.725 millimeters per second squared. Okay, and this here is what the book was, or not the book, sorry, the video was talking about when they said how far does the moon fall in 1 second. And if you say you go with this acceleration and you plug in d is 1/2 times that acceleration of the moon times 1 second squared, you get about, let's see, you're going to get 1/2 of this, right? So 1.36 millimeters, which is around 1/20th of an inch. It's not all that close, but it's reasonably close, and that's where Newton got his whole 1/20th of an inch thing, okay? But it's easier for us just to compare the acceleration to what it should be. So now we know the acceleration of the moon in its orbit is 0.002725 meters per second squared, and the period, no, wait, we don't know the period. We do know the period, but I want to show you how we can get the period. The distance of the moon from the Earth, which is the radius of the moon's orbit, right, is 384.4 times 10 to the 6th meters. And so we can find the, let's see, how do we find the period of the moon's orbit? Well, we know that the acceleration for an object in centripetal motion is equal to omega squared r, or sorry, uniform circular motion, not centripetal motion. So we can solve this for omega. Omega is square root of a over r, and what that gives us then, that gives us omega equal to, if I remember this right, 2.662 times 10 to the minus 6th radians per second. And that seems, wow, that's a really small number, right? Well, it makes sense. The moon has to go through 2 pi to do 1 full orbit around the Earth. It takes almost a month to do that, so the rate of its angular velocity must be very tiny. So you can then plug that into t equals 2 pi over omega, and that gets you the period of the moon is 2.36 times 10 to the 6th seconds, which equals 27.3 days, which is exactly what it is. So anyway, that's how that all ties together.